11.4, the final section of the course, area and arc length and polar coordinates. So we're going to use the polar coordinates that we learned about in the previous section, section 11.3, and do classic calculations, classic calculus 2 calculations about finding areas of regions in the plane, finding arc lengths of curves and stuff like that. And once again, this is a bit of a prelude. It's a bit of a prelude to multivariable calculus, when we'll do even more integrals and double integrals and things like that in polar coordinates. That's section 15.4 of the textbook. Okay, so what's going on here? So let's just draw a picture. So we have some xy axes. And so let's suppose that here, this is a function of theta. So we have this curve is going in polar coordinates here. So we want to think about what is the area of a sector. What's the area of a sector here? From this would be some angle alpha. And let me use a different color here. This would be some angle beta. And so we're trying to find the area of this sector right here. In some sense, this is, what's our classic phrase from, earlier in this course, or at the very tail end of Calculus 1, the quote-unquote area under the curve. Well, it's not really an area under the curve, because this would be the area under a curve, and we're looking at something else. But if I rotate things, we do see it's kind of the area that is radially between our polar coordinates curve and the origin. So area under the curve, we are thinking about those kinds of questions here. So we're going to, our goal is to come up with some integral that will express this area as somehow using alpha, somehow using beta. Spoiler alert, it's going to be an integral from alpha to beta. And it's going to have to use the particular formula here. R is a function of theta. Well, we're going to want to chop up to small little chunks here. And it's going to be chunks that are small little wedges moving towards the origin. So we're going to, have go chunk, 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 and we're going to look at each one of these little wedges here and figure out what's going on. So let's take a look at one of those just little wedges. I'm not going to draw exactly to scale, because I want to have the big picture for what's going on here. This is going to be, what's the angle here? It's kind of like, this is going to be just a little change in theta. So if, theta 1, theta 2, this is the change in theta. So that's what's going on here. And then out here, what is this out here? This is f of theta. I mean, maybe we're indexing theta sub j or something like that to be formal here. We're approximating the overall function here. The overall radius was just the calculation at a particular point. Well, what's the area of the sector? What's the area of from here to here? What's the area of the kind of pseudo triangle bounded by this, this, and this? So high school geometry tells us that this has area equal to 1/2 times f of theta squared times the angle delta theta. Maybe I should be sticking a theta sub j here, because at this point what we're going to do, turn this into a Riemann sum, kind of thing. We are going to add up over all j. we're going to add up all of the areas of all of those little wedges, and we end up with the sum over j of 1/2 f of, oops, what did I forget? I put a squared there. I didn't copy down that square. F of theta j squared, delta theta. So when we take the limit, the sum becomes an integral. The 1/2 moves outside the integral. This just becomes f of theta squared. The delta theta becomes a d theta. And we are integrating from alpha to beta. So if you want to see the textbook for more formal derivations of this formula, you can. But here is our first theorem. So this is area in polar coordinates. If f is a continuous function, the area bounded by a curve in polar form, r is f of theta, and the raised theta is equal to alpha and theta is equal to beta. We're assuming alpha less than beta is exactly this right here. 1/2 times the integral from alpha to beta of f of theta, all of that squared, d theta. Okay, so for one final time in the course, we've seen this kind of Riemann sum idea be able to give us this overall calculation. And so in the next couple of videos, we'll do some applications of this formula.